All right, so as we saw in the previous part, that the work net done will be equal to the final kinetic energy of the object. So we know that work is equal to KE final, where KE final is 1/2 mv squared. Which means that if I can measure the mass of the object and I can measure the speed of the object, so again, the mass, which we will want in kilograms, and the speed, whose unit is in meters per second. If I know these values, I can calculate the final kinetic energy of the object that I'm doing. Well, the mass will be straightforward. If you look in the cards, there will be a table of masses. You'll need to look up which car you have, and then use the mass of that. In addition, we've given the mass of the little sensor, the Pocket Lab sensor. You'll need to know that too, because you have to think about what is the total mass of the thing that's moving. And the following video where we walk you through the experiment will maybe help you make that make sense. So the question is how do we get speed? Well, if you think back to the previous lab, the last part of that lab, we had you measure, move your hand toward and away from the sensor at a constant rate. And that then gave you data that was the range, in other words, how far your hand was from the sensor over the time as a function of time. And so here might look what your data might have looked like, that if you moved your hand steadily toward the sensor, you end up with data that looks kind of roughly like a line. And so we talked a little bit in the last part that, well, if we fit a line, we would say that the function y is equal to mx plus b, where again, m was the slope and b was the intercept. And we walked you through how to do that, and I'll do that again in the next video. So if we fit this to a line, this line would have an intercept where it hits the y-axis, and it has a slope. For the moment, what I want to do is focus on the slope, this term right here. We said the definition of slope was the rise, in other words, the amount that the y value changes, divided by the time, delta t. Run. So this is rise, and this is run. Delta y over delta x. Well, in our case, delta y is the range. So it will be the change in the distance you are from the sensor, and the x-axis is time over delta t. Well, if you think back to lecture, change in distance over change in time was the speed. So by fitting the data that we're going to acquire to a straight line and determining what the slope is, that is what will tell us the speed. So what you're going to do, and we'll walk you through in the next video how to do this, is select the region where the car is moving at a constant speed. You're going to be recording range versus time, or position versus time. You're going to extract the region where it's linear. You're going to fit that to a line, and you're going to record the slope. And in recording the slope, that you really are going to be doing is recording the speed. Now we're going to have you do this 3 times. And the reason for that is, for each distance you pull it back. And the reason for that is that we're going to take multiple measurements at a particular distance, because that helps reduce any error that is in the experiment, that if you maybe pulled it back a little too far or a little too short, on average that will come out. And so you're going to record 3 slopes, which will represent speed 1, speed 2, and speed 3. And then we're going to want you to average those values together. And how do we do that? Well, V average will be equal to, and the little bar above the V means it's the average, will be equal to V1 plus V2 plus V3 all over the number of points that you're averaging together, which in this case is 3. If I had a fourth velocity, I would have plus V4 and divide by 4. And that will be your average velocity. So just to summarize, we're going to acquire range as a function of time, just like you did with your hand, except we're going to use the cars. And by finding the slope of those values, we are going to be finding the speed that the car is moving. That's why we're taking that data and fitting it to a line. And again, the slope being rise over run is change in position over change in time, which, as you learned in lecture, is the speed. You'll be doing that you'll be taking 3 measurements for each pullback distance, and you'll be averaging those values together. And that average value is the one that you're ultimately going to want to use to calculate the kinetic energy from 1/2 mv squared. So that is our particular experiment, the way we're going to analyze at least the first part of the data for our experiment.